Hi. Before we get started, I'd like to thank the organizers of GopherCon EU for putting on this event. I greatly appreciate your dedication to the community during times like these when it's certainly needed the most. My name is Alan Braithwaite, and I currently work at Segment, which was acquired by Twilio last year. Now in this talk, I'm not going to tell you exactly why it takes a team of engineers to build a real-time event pipeline. Instead, I'm going to show you what we built and how we got there. From that, I hope it will be clear that it could not have been done alone. Great infrastructure requires effective planning and coordination across teams that share a common goal. It is my hope that by sharing our journey, it will inspire other organizations to adopt patterns that will drive their engineering culture forward. You should walk away from this talk with a good high-level framework for building these systems using Go in your organization, as well as a real-world example of a highly scalable, event-driven infrastructure. Real-time processing is no small feat. There are a number of challenges to building such systems, including availability, consistency, handling state, cost effectiveness, among many others which are hidden in the details. This talk is broken down into 3 parts, each of which addresses some aspects of these challenges. The first of which is architecture, and I'll go a little bit into detail about how our architecture has evolved to become more reliable. Second, we'll go into detail about some of the systems that we've built and how they handle some of the challenges that we face today. Finally, we'll talk about the secret sauce that brings it all together and makes it all possible. So first is architecture. When I started at Segment, naturally one of the first things I did was look at their GitHub profile and see what's going on with the repository situation. So there were thousands of repositories, and many of them actually had associated services. So I would say that the general attitude towards microservices around that time was just that they were amazing and they would solve all the world's problems, similar to cryptocurrency today. Instead, the reality was more like this. Now, that's not to say that Segment was a complete dumpster fire. Even though we did have some pretty bad outages, it was still in a good place and people wanted to go the right direction. And for that, we're very thankful for our customers' patience at that time. So why are microservices so painful to operate? Let's take a look at an example. So here we have a simple microservice architecture with 6 microservices. This in and of itself is not that complicated. It's fairly easy to reason about, at least at this level. But let's go into a little bit more detail. If there is an outage or some sort of network partition between service D and service F, this can happen for any number of reasons. It could be a normal release where perhaps the health check isn't handled properly, or maybe there's a bug in service F that causes a crash, or possibly, dare I say, it could be DNS or service discovery. The root cause of this failure isn't actually that relevant in this situation, because if service D has a hard dependency on service F, then it necessarily is going to go down. And if service D goes down and service A has a hard dependency on it, then service A will also go down. So if we, for a moment, assume that the uptime for service F is 95%, to use an extreme example, then it should be clear, at least I hope it's clear, that the uptime for the entire system cannot be above 95% in the best case. The reality is actually worse, though, and to analyze why it's bad, let's do some math and think about what's going on here. So if each service can fail independently and the other 5 services have, for example, 99% availability, then, and we assume that the total uptime if we assume that each service can fail independently from one another, then the actual availability for the entire system cannot exceed 90.3%. Even if each service in that architecture had 99% availability, so 2 nines of availability, if you will, then the uptime cannot exceed 94%, which is still pretty bad. So if we take it out to 3 nines of availability for each service, we'll still have 54 hours down per year, which is really not great, especially if you're trying to break into enterprise markets. I hope it's clear from this that microservices that depend on each other really create this problem. And so we needed to think about how we were going to address it. So of course the solution was to get rid of microservices. So we were at a turning point in Segment's lifetime around this time. We were growing at a rapid pace, and as a result, we weren't delivering the reliability that is expected of a company trying to break into enterprise markets. So essentially, this post was one of the first projects that we did to attempt to bring our reliability up to reasonable standards. Essentially, what we did is we consolidated our repositories and our service for integrations that talk to our various partners into one domain service whose responsibility was simply to handle those external connections, but could easily scale horizontally. So the idea here is that it has one responsibility, but it's not necessarily single purpose. We realized that this pattern could be repeated elsewhere throughout our infrastructure, that is, consolidating microservices into single domain services in which the domain is clearly defined, but not necessarily single purpose. So the effort in this post drastically improved our availability for integrations, but there's actually another architectural change that we made that relates to domain services that I want to go into more depth about. But before we do that, I want to give some background first. So for those unfamiliar, Segment is effectively an event broker for the internet. Here is a conceptual architecture of Segment. Essentially, we have an inbound API that accepts events from the internet. It accepts events from clients, which can be anything from phones to browsers to other servers. After it's received by the inbound API, we put it into a queue, which is then consumed from, and some validation and processing is done on those events. After that, we put it into some more queues, and eventually it makes it to our outbound integrations consumer, which is responsible for sending those events to our partners and external APIs. Essentially, this is what the architecture looked like in practice when I joined. So each of these stages of the pipeline actually has dependencies, external dependencies in our infrastructure, which were essentially other microservices. And these microservices themselves could have other dependencies as well. So we had the situation where microservices were depending on other microservices, and it became kind of a tangled web of dependencies. Just like the first example I gave with microservice availability, if any one of those dependencies failed, then it would cause either a halt in the pipeline or a massive slowdown and reduction in throughput. I'd like to note that it doesn't even have to be a complete outage of one of these services to cause a massive slowdown in the throughput. Even a spike in latency, talking to one of these external services, can cause a reduction in throughput. So that's important to note and came into consideration when we were designing a solution. So we all got into a room and brainstormed what we could do about this solution, about this problem rather. And essentially what we settled on was taking a page out of networking books, and we decided that we were going to separate the control plane and the data plane. So up at the top, you can see our data plane, which is the original data plane that I showed you. And on the bottom, we've replaced it with a single database we call control store. And so this effectively becomes our control plane. Now, control store is a highly available, eventually consistent, read-only database that operates inside every host in our infrastructure. So this looks pretty, but how does it actually work? So this is how it actually works. Essentially, control store is a distributed database where every host has a SQLite instance with the read-only configuration, customer configuration data. That SQLite instance on every host is then mounted into every container that needs to read it so that the processes can access it in a read-only manner. To populate the local SQLite database, we have a reflector which essentially consumes the data from the system of record, which is the control DB in this diagram, and populates the SQLite database. To get data into the system of record, we have all our domain services write via their loaders into the executive service, which is what's responsible for writing into the control DB. Essentially, this enables us to distribute customer configuration data in a highly available manner throughout the entire infrastructure. So failure of any one of these upstream does not necessarily imply a failure of the processes inside the data pipeline. And so essentially, because the data is local and it's low latency to read, that resulted in a massive improvement in our reliability in the core pipeline. Of course, the devil is really in the details here. It took a significant amount of effort from all our teams in the organization to actually migrate every service into their own domain services and have their loaders reading from their systems of record to be put into this control store. So I'm happy to say that it's actually open source. It's written in Go, of course. It has a fancy website, and I highly encourage you to check it out if you have this kind of problem in your own infrastructure. So key insight here is really to, if you're operating a highly scalable data pipeline, then you should attempt to separate your control plane from your data plane. And if you're not operating in a data pipeline, then maybe you could consider at least separating your write path from your read path so that your read path isn't necessarily blocked by outages. So now I'd like to talk about some specific systems that we've built in order to address some of the challenges that Segment faces operating our pipeline. The first I'll talk about is how we handle duplicates. So of course, just like this photograph, there are many valid reasons why we might be receiving duplicate events coming in through the front door of our pipeline. Aside from that, though, if we have services which we wanted to design the system so that even if there are services which crash and come up and produce duplicates, they can operate in an at least once manner so that we don't have to design every system to produce exactly once. So we needed to build a mechanism to deduplicate the events. So we put our deduplication right before our destinations to ensure, once again, that if we have failures in the pipeline, it can be handled cleanly before we send it to our partners. That doesn't mean that we never send duplicates to our partners, of course. In fact, most destinations don't actually support transactional delivery, so if we lose an affirmative response for whatever reason, then we're forced to try again and fall back to at least once delivery. So how does that system work? Conceptually, it's not that complicated. We have an input topic and an output topic. These are on Kafka. Each topic has messages in it. Each message has an offset and a message ID. Then we have a consumer with a local RocksDB keeping track of which message IDs have been seen. And essentially, the process is this. We consume a message off the input topic. We first check to see if that ID exists in the local RocksDB instance. If it does not exist in the local RocksDB, we produce it to the output topic. And here's the key thing to notice. We produce it to the output topic with the input offset. So the input offset lives inside the output topic with the message as a piece of metadata. We then commit that ID to RocksDB, and then we commit that offset back up to the input topic. So essentially what this enables is if we have a failure after we've produced to the output topic, so in steps 3 or 4, we can recover cleanly. And you'd be right to ask, well, how does that work? Essentially, recovery is like this. You read the upstream offset, and you read the downstream input offset, and you take the difference between those two offsets, and that essentially means that represents how many messages you need to read from the output to check their IDs. And the reason why this works is because if there was a failure anywhere between step 2 and step 4 here, then essentially what that means is that output offset, or the input offset in the output topic, has the true, we've already produced that message. It is the system of record for what's been produced. And with that offset, if there was any failure before 4 was committed back upstream, then we can just simply read the input offset and know that we need to consume that many messages from the output. So then we scan that many messages and ensure those IDs from the output topic are committed to RocksDB. And finally, we commit the topic back upstream before we continue consumption as usual. So I know that's a lot to digest. You can ask me more about that after the talk. However, I do want to highlight that the key insight here is you can use your destination topics or databases as pseudo write-ahead logs to recover from failures. If you know what's in the output topic and how far you've consumed from the upstream, then you can always recover by reading what's already been written to your system of record. So we actually use this strategy in another key domain system, which is relatively new, and that domain system is ClickHouse. We have a number of products which need to calculate high throughput, high cardinality statistics in near real time. Previously, each product would basically implement bespoke counting and aggregation services using Go and Redis, and essentially they all became very difficult to maintain. So we chose to use ClickHouse. Now, I had experience with ClickHouse from Cloudflare, and I knew it would be a good fit for this just from that experience, but the reason why it's so effective at building these types of applications is because it enables high throughput writes using a log structured merge tree columnar data format. So you can write as fast as you can to these databases, and it will be able to handle the inserts. The other thing that it does is it enables high performance, high cardinality, near real-time analytics through its somewhat novel materialized views. Now, materialized views exist in other databases, but essentially the way that they're designed in ClickHouse allows you to build aggregations that can be persisted for longer without having to keep around the raw data. Finally, it's also highly available and it has a multi-leader architecture, so it really satisfies all of the scalability constraints that we need to satisfy. One pattern that we use to put around databases, and this isn't necessarily unique to ClickHouse, but the way that we access ClickHouse from other services is actually through something we call a query gateway pattern. So the idea behind a query gateway pattern is that you have a domain service for every database that you operate. And the reason why you have a domain service for every database, and the reason why it's relevant to ClickHouse, is because it doesn't allow other clients to randomly connect to the database and run their own queries. Those queries might have performance or security implications that we don't want that we want to be able to control at the domain service level and not at each individual service that's consuming the data from the database level. Additionally, it allows for easy audit trails because we can use the same HTTP middleware to log and indicate who is accessing the database and what services are accessing the database. Finally, perhaps the biggest hidden benefit is it allows the domain experts, in other words, the people who have the most experience with that particular database and dataset, to code review the queries that are being run against the database for security and performance implications, and also ensures that the database is used for its single purpose and not for any random purpose that might not be as easy to audit or debug. So finally, the section I'm sure you've all been waiting for, the secret sauce. Now, I'm sure it should come as no surprise to any of you at this conference that the secret sauce is indeed Go. Now, I'll talk in a moment about what specific features of the language we found most useful to building our services. But first, I'd like to give a huge shout out to our team at Segment. Our internal engineering culture shares a lot of the values that the Go community and project embody, which I believe is ultimately what enabled us to accomplish all that we have. If you ever want a template for how to build a culture which fosters learning, innovation, and inclusion, you have no further to look than Go's own code of conduct. So thank you, teammates, for exemplifying this behavior and making Segment a great place to work. With that, let's talk about some specific Go features that I believe helped us on our journey. So first, I have an example. I pulled an example from this library, which isn't open source, but was fairly instrumental in enabling a migration that was pretty big for us. So back in the day, we used to use NSQ, which served us well up to a certain point, but we really needed a much more scalable platform for building services, and we wanted to migrate to Kafka. Essentially, this was a core and key abstraction on top of all our queues at Segment. You'll notice that it's relatively simple, and each interface only has one method. The message is a very straightforward struct with not many fields. And ultimately, the simplicity of the interfaces and the absence of inheritance is what makes this so powerful. Other languages have interfaces, of course, but there are none that I'm aware of that are as simple as Go. And before Go, I really never appreciated the power of declaring an interface. But because Go isn't object-oriented and doesn't have inheritance, it really forced me to change how I think about the expected behavior of the code. So when you go to write an interface, it really makes you think about what the very essence of the behavior that you're trying to describe is and what you want to support. So in this particular case, it was very powerful in describing these queues and really enabled us to build that migration. It really enabled us to execute that migration after updating the code to use this library. So this library, unfortunately, isn't open source. You can see that the value field of the message is a byte slice. Ideally, we'd like that to actually be a generic type because there is really too much serialization going on around that value that we'd like to not have being done. The next library I'd like to talk about is actually an open source library. So the library is segmentio stats, and it's effectively the single library that we use for all of our metrics collection. So whenever we need to export metrics from a service in our infrastructure, we use this library. And it was built with performance in mind. And the reason why I wanted to talk about this in particular, the feature that Go provides, is that it really provided the tools for analyzing performance. Now, with any kind of observability library, you want it to be as close to zero overhead as possible. And without those tools, I don't think building this would have been nearly as effective. So it additionally uses a simple interface. And because of that, and because of the tools for performance analysis, we were able to implement destinations for Datadog, InfluxDB, Prometheus, and Stripes Veneer. Finally, the last feature of Go that I want to highlight is the importance of stable APIs in Go. So I see Go being boring as a feature and not a bug. Essentially, if APIs were not stable in Go, then we wouldn't have been able to build this library, which is a drop-in replacement for encoding JSON. Because we use and operate mostly with JSON events, we really needed to make sure that the processing of those was as efficient as possible. So this library results in a 60 to 400% performance improvement over the standard encoding JSON. However, we don't actually believe that this code is necessarily appropriate to upstream. It is fairly complex, and one of the key important tenets of the standard library is that it's easy to maintain. And without that maintainability and without such a strong reference implementation in the core library, this wouldn't have even been possible. So thank you to everybody, the entire team at Segment and the Go community. It's really an honor to work with such an effective team and be a member of this community.